right, welcome everyone. Today we're going to continue talking about trigonometric substitution. Just look at a few more examples, maybe a couple harder examples than the one we looked at before, just to kind of see some variety in things that we might encounter while we're going through a trigonometric substitution. All right, so we're going to get started here on our second example for this topic. And this is the integral of the square root of 25 minus x squared divided by x squared. So the first thing we need to do when we are going to do a trigonometric substitution is to decide on what we should pick for x. And if we remember back, there's really three choices. And when we see something of the form x squared, oops, that's not the one we see. We see a squared minus x squared. So we have a trig expression of that format. And so when we see something of that form, this is where we let x equal to a times sine of theta. So that's what we're going to do here. We're going to let x equal to this sine function. And the only thing that's kind of required of us, once we kind of have the framework for what we're going to pick for x, is there's a little bit of work on how we actually decide on what a is. And so the way we do that is we look at the constant term, and a is just the square root of that constant term. So square root of 25 is 5, so we're going to let x equal 5 times sine theta. All right, so that's really the first bit of our work. Then there's two other ingredients that we can kind of calculate right away. And that's our differential dx, and then the square root term. So what's dx going to be? Well, just the derivative of 5 times sine. So that's going to be 5 times cosine theta. And then we multiply by d theta. And then what's the square root term going to become? And you can work through all this. We did a couple times yesterday where we worked through all of this, used some trig identities, simplified it down. But really, it's just going to become the opposite of our sine function. So this is just going to become 5 times cosine theta. And you can check that for yourself. So use our trig identity. Really, there's some behind the scenes work that we looked at yesterday. It's always going to be producing the same results. So you can check this by using our trig identity. Sine squared plus cosine squared is equal to 1. All right, so there we go. We have all of our pieces. So now we go up to our integral, and wherever we see an x, we're going to change it to 5 sine theta. Wherever we see a dx, we're going to change that to 5 cosine theta, d theta. And if we see any square root terms, which we should, we're going to change that to 5 times cosine theta. So let's plug in all our pieces. And this is kind of the fun part. You get to change everything, and then maybe there's some canceling. Who knows? Let's see. So let's start with this square root term. That's going to become 5 times cosine theta. What about in the denominator? Well, this is going to become 5 times sine theta squared. And then the dx, we know what our dx is. That's going to become 5 times cosine theta. And there we go. We end up with this expression, 5 cosine theta over 5 sine theta squared times 5 cosine theta. And when you're going through this, you just want to kind of keep track of the constant terms. It's easy to kind of lose track of one of them or forget that, for instance, in this 5 times sine theta, this whole thing is being squared. So we actually have 2 copies of 5 down here, and we're going to have 5 copies in the numerator. So there is going to be a little simplifying. So we can take this cosine term, we can take this cosine term, multiply them together to give us cosine squared theta. Then we have 2 copies of 5 in the numerator, and we have 2 copies of 5 in the denominator. So those are going to cancel. And so we're left with cosine squared over sine squared d theta. So now essentially what we've done is we've taken this integral involving a square root, we've done our trig substitution, we've cleaned it up a little bit, simplified a little bit, and now we have this trig integral involving powers of sine and cosine. So there's different ways we could handle this integral here. Cosine over sine, we could convert this to cotangent. So that might be an option. Convert it to cotangent squared, and then try integrating cotangent squared. One other thing that sort of jumps out at me is we have this sine squared plus cosine squared identity, and I see a cosine squared in the numerator. So let's see what happens if we use this trig identity to kind of simplify this fraction. So instead of cosine squared, we could write 1 minus sine squared all over sine squared. So this is just a different way of doing it. A lot of times with these trig integrals that we get, there's various ways you could go through it. So if you want to try the cotangent squared method, give it a shot. That one's equally as good. We're trying something slightly different here. We're using our usual sine squared plus cosine squared trig identity. And when we see this, we have 1 minus sine squared all over sine squared. So we can actually break this up into two separate fractions. So 1 over sine squared theta minus sine squared theta over sine squared theta, d theta. And we can simplify. So sine squared over sine squared is going to simplify to just 1. And 1 over sine squared, that simplifies to cosecant squared. So when we go through the simplifying, we end up with cosecant squared minus 1. And this is one of our elementary form integrals. This is just one of our basic integrals we should know, or at least recognize that it is and maybe look it up. And then we also have minus 1, and that should be easy to do. So cosecant squared, the integral of that is negative cotangent theta. The integral of minus 1, well, that's not too bad. That's just minus our variable, so minus theta. And then we put plus c. So there we go. We've kind of gone through most of the work. We have our antiderivative. And now the last step here is to convert back to our original variable. And this is where we're going to use our right triangle, and we're going to use our original trig substitution to help us figure out what the sides of that triangle are. All right, so let's do that over here. So far we've found that this integral is negative cotangent theta minus theta plus c. And our substitution was x equal to 5 times sine theta. And so to figure out the sides of our right triangle, let's draw that in. There's theta. We're going to start with our trig substitution, and we're just going to solve this for sine. So sine of theta is x divided by 5. And we also know that sine, what sine is in terms of the different sides of our triangle. So sine is opposite over hypotenuse. So that means the opposite side has length x, and the hypotenuse has length 5, if we just compare these fractions. So our opposite side has length x, the hypotenuse has length 5, and what this means is the missing side, the one we don't have here, that's actually just our original square root term. So that's just the square root of 25 minus x squared. And if you want, you can check that. by the Pythagorean theorem. So what is the Pythagorean theorem? Remember, a squared plus b squared is equal to c squared. Or if we write it out for our specific sides, it's the opposite side squared plus the adjacent side squared is equal to the hypotenuse squared. So you can do a little quick check to actually see that the missing side is just our original square root term. And that's going to be the case for all of these. So you use your original trig sub to figure out, the simple sides, and then the missing one is just whatever square root term was originally there. All right, so let's now look at what we actually need. We need to know cotangent, and so we can do that. Cotangent theta is the reciprocal of 1 over tangent theta. And actually, I'm going to do this down here because I'm going to use this space. We're going to use this space for, we're going to use this again, this sine theta equal to x over 5. We're going to use that again to help us figure out this kind of lone theta term. But let's figure out cotangent first because we're working with our right triangle. So cotangent theta it's the reciprocal of tangent. So normally I remember that tangent is the opposite over the adjacent. So cotangent is just going to be the reciprocal of that flipped. So it's going to be the adjacent side over the opposite side. And if we look on our triangle here, the adjacent side is our square root term. So square root 25 minus x squared. And then the opposite side is x. So we've figured out what cotangent is. Now we need to figure out what this lone theta is. And to do that, we're going to use our original trig sub. And we're going to solve this using an inverse function. So we have this equation, sine of theta is equal to x over 5. Well, we have an inverse sine function that allows us effectively to kind of move this side. We really want to solve for theta here. So we really kind of want to somehow get this sine term, this sine expression, whatever this thing is, we want to get it on the other side. And for functions, the way we can kind of cancel off functions is with their inverse function. And inverse sine is going to help us do this. So we apply inverse sine to both sides of that equation. And on the left, the inverse sine and the sine function cancel off. And that's just going to leave us with theta is equal to inverse sine of x over 5. So we're kind of getting a little bit of practice here doing it all. So this is one way for kind of solving for these lone theta terms. We can use an inverse trig function. But then solving for these trig functions, we can use our right triangle and get a more compact form, more compact expression here. So now we have all the pieces. We know what cotangent is. We know what theta is. Let's just plug everything in. So cotangent is negative square root 25 minus x squared over x. And then the theta is minus arc sine of x over 5. And then we have our plus c. All right. So that's kind of, we're seeing, slightly more things here, more slightly different ways of converting back to x. Let's try another one. Let's look at example 3, and here we're going to integrate 1 over x squared times the square root of 4 plus x squared. And so when we look at this, we're seeing a square root term of the form a squared plus x squared. And when we do that, when there's a plus there, that's our tangent one. So we're going to let x equal a times tan theta. And the way I kind of remember it is the plus kind of matches up with the t. I don't know. It kind of looks, that's how I think of it. The t kind of looks like a plus. So there we go. And let's kind of write down our pieces. And so the only thing that we have to figure out then, once we decide on what our trig sub is going to be, is to figure out a value for a. And to do that, we look at the constant and just do the square root of it. So we have 4. Square root of 4 is 2. So this is going to be 2 times tan theta. Then we need to differentiate that to calculate dx. So derivative of tan theta is 2 times secant squared theta d theta. That's the derivative of tan theta. And then we also can know what our square root term is going to be. It's just going to become the opposite of whatever this trig function is. And when I say opposite, I mean opposite in relation to kind of our usual trig identity. So for secant and tan, it's secant squared is equal to 1 plus tangent squared. So I kind of, based on this identity, I kind of think of secant and tan as sort of opposite functions. Same thing with like sine and cosine. In the last example, we had sine squared plus cosine squared equal to 1. I kind of think of sine and cosine as opposite functions based on that trig identity. So here, x is 2 tan theta. We could run through this whole thing, using this trig identity, but what we would end up seeing is just this square root term is just going to be the opposite trig function based on this identity. So it's going to be 2 times secant theta. All right, so we have all of our pieces now. So let's just plug everything in. So we're going to have the integral of 1 over, instead of an x squared here, we're going to do 2 tan squared. And then instead of the square root term, we can put in 2 secant. And then finally, instead of dx, we can put in our 2 secant squared theta d theta. Again, you just want to pay attention to the constant terms. So there's actually two copies of 2 times tan theta here. So there's actually 2 copies of 2 here. There's a 2 here. There's a 2 here. And let's go through and cancel as much as we can. So this one we're going to be able to do some canceling. So let's get out the red pen. We can cancel off the 2 here, cancel off the 2 here. And then there's 2 copies of secant squared here. There's 1 copy of secant in the denominator, so we're going to be able to cancel that secant out. And that's it. That's as much simplifying as we can do. So let's kind of consolidate everything, clean this up. We end up with secant theta over, and let's multiply all this out. So we're going to have 2 squared, which is 4, and then tan squared in the denominator. All right, so there we go. We've essentially doing this trig substitution. We've taken this integral where we had a square root, and we've converted it into a nice trig integral where it's just powers of secant and tan. So now we need to decide how we're going to integrate this. And, normally our quicker ways for doing a trig integral involving powers of secant and tan are, can we factor off a secant squared? So do we have an even power of secant? No, not for this one. I mean, maybe we could get creative and kind of figure something out, but nothing obvious here. And the other choice is, could we factor off a secant theta times tan theta? That's how we generally handle these. These are our two things we're looking for. Can we factor off a secant squared, or can we factor off a secant theta tan theta? And we can't do that one either because we only have a secant in the numerator. So none of our usual strategies for powers of secant and tan are going to work here. So a good backup is, let's just try to convert everything here to sines and cosines. So let's do that. So instead of secant, and I'm going to bring the 1 over 4 in front of bring this constant 4, I'm going to put that in front of the integral. Let's simplify that secant term. So secant becomes 1 over cosine theta. And then what's the reciprocal of tangent squared? Well, tangent is sine over cosine. So the reciprocal of tangent squared is going to be cosine squared over sine squared. So the 1 over cosine, that's our secant. And then the reciprocal here, the cosine squared over sine squared, that's our 1 over tangent squared. So we just kind of broke things up. And now we see that there's a little bit of simplifying we can do. Some of the cosines actually cancel. So that's going to be good. So going a little bit further here, we have the integral of 1 over 4. And then inside we have cosine over sine squared. And now when we look at this, now we've converted it into a trig integral where we have powers of sine and cosine. And for powers of sine and cosine, we're looking for either an odd power of cosine or an odd power of sine. And we see an odd power of cosine here. So that's going to be good. We can use one of our usual kind of strategies, our trig integral strategies. So when we do this, looking at this integral, we're going to do another substitution, this time a u substitution, where we're going to let u equal sine theta, and du is going to be cosine theta d theta. And so the whole reason why this method is going to work is because we have a lone cosine theta, which we can kind of group with this d theta, and that's just going to become our differential. So we're going to have 1/4, and then the division by sine squared with this substitution, that's going to become u squared. So we're going to have 1 over u squared du. And that's something now we can do. That's just a power function. So the antiderivative of that is negative 1/4 times 1 over u. And if you needed to, remember we can rewrite our function here as u to the negative 2 to help us with that integration. So it just becomes power rule. And then put our plus c. And then the last thing is we want to convert this back to our, well, we're going to do a couple conversions, but we're doing a u sub right now, so we have to convert back to sine theta. So this is going to be negative 1/4 times 1 over sine theta plus c. All right, so there we go. There's our antiderivative so far. We still have to get back to our original variable. So far we've done all of this. We did a u substitution. We converted back from that, but we still have to convert back from our original trig sub. So let's try that now on, there we go, over here. So let's write down what we have so far. We have our integral is negative 1/4 times 1 over sine theta plus c. And our original trig substitution was x equal to 2 times tangent theta. And this is going to be enough for us to fill in our right triangles. So let's start by filling in our right triangle. Here's our right angle, here's theta. And let's solve this equation here for tangent theta. So we get x over 2. And we know tangent theta is also the opposite side of our right triangle divided by the adjacent side. So if we just match up these two fractions, the numerator here is x, the numerator here is our opposite side. So that tells us the opposite side of our triangle is x. And then the adjacent side here, the adjacent side here and the denominator here, those are both in the denominator, so our adjacent side is 2. And you could check it, but the missing side is just our original square root. So it's the square root of 4 plus x squared. Again, check this with the Pythagorean theorem. Good little practice there. But it's just going to be our missing square root term. All right, so now in our function here, or in our antiderivative so far, we have 1 over sine theta. So let's figure out what sine theta is. It's the opposite side over the hypotenuse. So the opposite side we said was x. The hypotenuse we said was square root, that square root term. And so that means when we do 1 over sine, it's just the reciprocal of this. So it's square root 4 plus x squared all over x. And then we just take this and fill it in up here. And that's our answer. So we're going to have negative 1/4 times the square root of 4 plus x squared all over x plus c. And there we go. We're able to convert back to our original variable. All right, let's try one more. So these take a little bit, but it's good practice. So let's try one more. Here we're going to integrate the function x squared divided by square root 4 minus x squared. So we're going to start by looking at what our square root term is. And if we look at this, we have the format a squared minus x squared. So when it's minus x squared, that means we're going to use x equal to a times sine theta. All right, so let's do it. And again, the first thing we need to do once we decide on which format to use, we have to figure out a. And a is just the square root of that constant term. So it's just going to be 2, square root of 4 is 2, times sine theta. Then we calculate dx. So what's the derivative of sine? It's cosine. So 2 cosine theta d theta. And then we also can just figure out our square root term as well. It's just the opposite trig function. So we know sine squared plus cosine squared is equal to 1. So because of this trig identity, I kind of think of sine and cosine as sort of being opposite trig functions. So since we're letting x equal 2 sine theta, the square root term is just going to become the opposite one. So it'll just be 2 cosine theta. And you could check this by just using this trig identity. We did that a few times yesterday. All right, so now we have all of our ingredients. So let's plug everything in. So in the numerator here, we have an x squared. So let's plug in 2 sine theta. So we're going to get 2 sine theta squared. In the denominator, we know what's going to happen with the square root term. It's just going to become 2 cosine theta. And then our dx, we need to convert that as well. So that's just going to become 2 cosine theta d theta. And we got a little bit of simplifying we can do. So this is the fun part. Get out the red pen and we can cancel off some 2's. We can cancel off some cosines. And when the dust settles, we end up with the integral of 4 sine squared. And there we go. Nice, simple trig integral to do now. So we went from this complicated function with a square root. Now we have this trig integral to do, just a power of sine. And it's an even power of sine. So we need to use our trig identity, and the trig identity we're going to use is one of our half angle formulas. So let's use that next. So instead of sine squared, we're going to write that as 1/2 minus 1/2 cosine 2 theta. And that's our half angle formula. We can simplify it, just kind of distribute the 4. So we end up with the integral of 2 minus 2 cosine 2 theta, d theta. And now we integrate each of those. So these are integrals we can do. So why does this half angle trig identity helpful? Well, it takes a sine squared, it takes a squared power, and it reduces it down to just a regular cosine term. So now we find the antiderivative. So the antiderivative of 2 is going to be 2 theta. And then the antiderivative of this cosine 2 theta term, this is one of our k-form integrals. So the antiderivative of that is going to be negative 2, 1/2 sine of 2 theta. So remember, with a k-form, the 2 theta inside the trig function stays the same, but then we take that constant that is inside, flip it, put it in front. And then we put our plus c. And then we can simplify this down just a little bit. So the 2 theta and then the 2 and the 1/2 cancel out, and we're left with just minus sine of 2 theta. And we want to convert all of this. Now the issue here is inside the sine function, it's not just sine theta, it's sine of 2 theta. And so using our right triangle is going to be difficult to convert this because the angle is not just theta. It's 2 theta. So when we use our right triangles, that really only tells us trig functions where the angle is just theta. If there's anything else, then we have to, it really doesn't help too much. But we do have a trig identity that allows us to rewrite this. So we can rewrite this sine of 2 theta using a trig identity as negative 2 sine theta times cosine theta. And so that's going to be helpful because now we just have these trig functions where the angle is just theta. So that's going to be handy. All right. So how are we going to be able to do this? Well, we're going to set up our right triangle. Sorry about that. We're going to set up our right triangle. And let's see how it is. So our angle is, what was our original substitution? X equal to 2 times sine theta. We're going to do our right triangle here. So here is theta. And then our right triangle, or right angle here is there. Let's solve this for sine theta. So that's going to be helpful. It's x over 2. So just divide both sides by 2. And from here, we know sine theta is equal to the opposite side over the hypotenuse. So we just match up the numerators x and the opposite side here. So they're both in the numerator. So that means our opposite side here is x. And then we just match up the denominators. So 2 and hypotenuse. So that means our hypotenuse is length 2. And then the missing side is just our original square root term. So square root 4 minus x squared. And now we have our triangle filled in. So now we can actually start converting all those trig expressions in our antiderivative. So what was our antiderivative? And it was, oh, I forgot my plus c here. So our antiderivative so far was 2 theta minus 2 times sine theta cosine theta. And I'll be honest, when I leaned off screen here, really wanted to double check this one. So this is correct. So I just wanted to double check that this was in fact our trig identity. So I always kind of forget what the constant is. I remember that it's sine times cosine theta, but I sometimes forget what this constant is. So the trig identity we used there was sine of 2 theta is equal to 2 times sine theta times cosine theta. So that's the trig identity we use there. And again, the reason why is because when we set up our right triangle, our right triangle only really helps us convert trig functions where the angle is just theta, not something different. So let's rewrite now. Fill this in over here, 2 theta. It's easy to forget some of these trig identities. So you just kind of, when you're working on them, just have a little list of all the different trig identities. Maybe do flashcards to help memorize them. But it's really easy to kind of forget these little things. So, just kind of have a list that you refer back to. That can be helpful when you're working on these problems. So we have our 2 theta. We have our 2 times sine theta cosine theta. And so we want to convert sine. We already know what sine is. We also want to convert cosine. So cosine is the adjacent side over the hypotenuse. So the adjacent side is square root 4 minus x squared. And the hypotenuse is 2. So we're going to be able to fill in x over 2 for our sine. We're going to be able to fill in the square root over 2 for our cosine. And then all that's left to do is figure out what theta is. And whenever we have a lone theta like this, this is where we use our inverse trig function. So we start with our original trig substitution. In this case, we've gone a little bit further. And we can just apply the inverse sine function to both sides. And when we do that, that gives us theta on the left side, and it gives us inverse sine of x over 2 on the right. So, those inverse trig functions can be helpful for finding these kind of lone theta terms. And so we have all the pieces now, so let's plug everything in. So we're going to end up with 2 times theta. But instead of theta, it's inverse sine of x over 2. Then we have minus 2 times sine theta. Sine theta was x over 2. And then the cosine theta was the square root term over 2. And then plus c. And we just simplify this thing down. So the 2's, some of the 2's here cancel. And we're left with 2 times inverse sine of x over 2. Minus x, actually, we're going to end up with one more copy here of 1/2. So let's put the 1/2 in front. So 1/2 x times square root 4 minus x squared. And there we go. Now you can see these problems, there's a little bit of work here involved. So there's a lot of, it's kind of a review of a lot of sections of material that we've kind of been covering. A lot of geometry, a lot of trig functions going on. So these problems really kind of review a lot of the topics that we've seen so far. All right, so that's going to do it for today. Tomorrow we're going to look at a few more trig substitution examples, just to see slightly harder cases where we might have to do a little bit of work with our square root function first. So far all of our square root functions have been of those three kind of basic forms. Next time we're going to see we might have to do a little bit of work with this to get it into that form. All right, so we'll stop there for today. Have a good rest of your day. We'll see you tomorrow. Bye.